Today we start discussing technically about optimization in machine learning. So it's imperative that we should speak a little about what machine learning is to give you an idea about the problems, and you will see how naturally optimization problems arise in machine learning. So it's very important to know what is the term machine learning means, because it has become such a buzzword. People can just keep on giving basically telling this or telling that. Wherever you can just drop the term machine learning in every thing, and people would be very happy with you. But preceding that subject was something called statistical learning, where statisticians had some data for which they had some observation or some information already, and they said that if I know this information, then if I have a similar type of data where the relevant information is not there, can I define a function which will be able to gauge that data. So given the input, I've got some data of which I know. So for example, I know a pair of xi yi's from some, to take and say maybe the height and weight of some people. They are coming say from normal distribution. Now the question is, if I am given a set of heights of people, can I tell what are their weights? Can I define such a function? Can I create a function when I put that weight of the unknown data which I have not seen, unseen data, it will give me a height. Okay. And that the output that function would give would not vary very heavily with what is there in actuality. So but when can, instead of building functions, just writing something mathematically, once we started talking about how to compute those functions, or rather have an algorithm do this job, you come into the field of machine learning. Machine learning is a kind of fusion between statistical learning and computer science. So I have written these notes up. You might be worrying why I have written this in handwriting, and because if somebody wants these notes, I can send it to the person. That is easier to start with. Otherwise, it will come on a blackboard where you won't see me again. So sometimes I'll come and we'll have a general discussion. So many things can be considered as a learning process. In fact, the linear regression technique, which many of you know possibly in statistics, is a learning process. To me, even an optimization process is a learning process. If you move from one point, one iterate to another, you are actually trying to find a function, or trying to find a way where you can improve the function value, right? So that way, even optimization techniques, in my view, is a learning process. But people might vary on that. People might have different opinion. So I will like to say that machine learning is an algorithm in this case, not just a function. An algorithm which will, machine learning process is to construct an algorithm which will learn something from a given set of data, and on a similar set of data where my attributes, final attributes, are unknown, it will tell us what the final attributes are. Maybe it's making a mistake when doing so, but the whole idea is to keep reducing the error. So it's an error minimization game in some way, which we have to do in a very effective fashion, and that becomes very helpful in many things that we do, right? So to design this lecture, I have depended on these two books which I have already shown you in my first lecture on this topic, which is by James Witten, Hasty and Tipshirani, Introduction to Statistical Learning with Applications to R, and this famous book Deep Learning by Goodfellow, Bengio and Courville. Now from this deep learning book, I was very tempted, and I did copy this definition, which is the attribute to Michel from this deep learning book. So computer program is said to learn from experience E with respect. So what do you mean by learning actually? What is the meaning of learning? So computer program is said to learn from experience E, operating in a certain environment, with respect to some class of tasks and a performance measure P. If its performance at tasks T measured by P improves with experience C. So as more and more data comes in, its it does a better job of telling you what the unknown values are, right? So we have to know what is, we have to figure out what is the meaning of this experience, what is tasks, and what is this performance measure. Let you don't need to get too much bogged about in these terms, and we don't have to hold to terms. One of the most important problems that we use in machine learning does is classification. So given a data, tell who is what, who is who's, and who is X and who is Y, to tell it, I mean, in a very rough language. For example, in a medical setup, for example, in a cardiology department, suppose you have the data, it's a very crude example you might think. For example, you have data of two blood pressure level, the upper level and the lower level of blood pressure, the total cholesterol level of a person. And you have data of 50 patients whom you know, among these who are heart patients, whom you give +1, and another whom you know that they are not heart patients, you get -1. So these values of the blood pressure and values of the cholesterol level, these are called features of the data. And this +1 or -1 is called a label or classification of the data. That I classify up, given you give me a set of blood pressure, two levels of blood pressure and cholesterol level, I'll tell you whether the person is a heart patient or not. That is what the algorithm should be able to do. Now, first 50 sets, I really know who is what. So I have to construct a function or design an algorithm which first will operate on this data and see how many mistakes it makes. Because here we know the answers. We know the value of the labels or categories, if you want to say. But now suppose I have some data for, I do not know whether I have data of another 50 patients, and I do not know whether these patients are having heart disease or not having heart disease. I only know their values. Now, can this algorithm tell me who is a heart patient and who is not, and also making very less mistake? In the time of online treatment, for example, in the time of pandemic, these kind of approaches becomes very important. So machine learning or classification problem has a very usefulness, a great usefulness in medicine, and that will be apparent if you read machine learning books. Now, as I told you that those values of the blood pressure and the value of the cholesterol is called features. So associated with every data, there's a feature vector x, x1, x2, xn, maybe the n features, and a label which can have say k different labels, k different categories. So given a feature vector, it can go into any of the k categories. So I have to find the function f. The classification problem is to find the function f, which is called a predictor or classifier, whatever you want to call it, such that it maps an element in Rn to any one of these 1, 2, ... k's. Okay. So we have to first talk about training set. So I have say 50 different people. So here I have m people, and for each of them I have n different datas. So I have an m cross n matrix. So here in the training set, I know from the first data the label is y1, which could be anything between 1 to k. For the second also I know what is the answer, label is y2 and ym. So these, for these k people, all these cases, all the labels are known, the values of y1, y2, ym are known. So such data is called a training data, because you are telling the algorithm, you see, now look at those values very carefully and see the labels. What type of values is telling you who is a heart patient? What type of value is telling you who is not a heart patient? So that's a very careful thing. So the algorithm has to observe that. Now I'll give him another set of data, 50 patients say, or m patients, whose blood pressure and cholesterol are given, the 3, in this case n is 3. Can you tell whether it is heart patient or not? Here k is 2, 1 and 2. So that's the game. So how do you construct that classifier is what the job of statistical learning or machine learning. So often we call this matrix that is formed here as a training matrix. The key idea is as follows: you construct a function and you put these values of x vector from the training vector, this n vector, say x of 1, which has these n components, x1, 1, x1, 2, x1, n. I put it in the function f and see what it gives me. Does it gives me y1 or y2, or does it give me y1? Maybe, but there's a particular value. Yes or no? Does it give me, in the second one, does it give me y2? Yes or no? We have to make sure that here in this training set, it has been able to give me the correct values most of the time. That would be desirable actually. Now you can say, oh, that's not a very big deal. I can construct such a function. So you construct a function f0x which gives me yi whenever x is equal to xi and 0 otherwise. But the goal of constructing this function f or the classifier is not to just handle the test set, a training set. It is to handle a test set which is unknown, for which labels are not known. Only the feature vectors are known, but the labels are not known. I need to know the labels, and that is why this function is constructed to automatically tell me the label. So it's kind of an automation of the whole thing. So now you construct such a function. This suffers from a problem of what is called overfit. Now suppose I have a test set of data for which I have all the x's, the feature vectors, none of them matches with those of the training data. Then such a function on the test set will give me 0 value, which is meaningless. It doesn't, the 0 is not any of the label. It is, the label is either 1, 2 or k. So such a function doesn't work. Such a function suffers from what is called overfitting. It overfits the data. It fits the data, so training data so perfectly that it doesn't really work at all on the test data. So the key idea of the function, to find a function f which will fit the training set with very less errors but can perform reasonably well on the test set, which we have not seen before. So let xi be a feature vector of a test vector, test set, and yi be the test set label. The test, so the error in the test case, which is the unseen data, is this one. So we really have to find a function f which will work very well on the test set. We will have a very small error on the test set. But the problem is that the labels of the test sets are not known to us. So this game cannot be played. We can't do this thing. So we have to find a function which, at least for this to start with, works good on the training set, because for the training set labels yi's are known. So this is what I will call the training error or square training error. So this error measurement is sometimes called the performance measure. So if a function, sometimes it can have a function minimize the training error very well. For example, this will make the training error 0, but will make the test error hopelessly bad. So that means that we need not find such functions with training error 0. We can find a function where there is some training error, but overall on the test set also it is working pretty fine. Maybe the tests in the test set, that error in the test set would be higher than the training error. That's what happens in general. But that gap between the training error and the test error is not very high, right? So that is what we have to aim for. So here it gets into a game of guessing and testing, looking at a given particular data and see what actually we can do. It's not that we can really just put on the automation and just forget and sleep. Things may not always work out well. So another type of task is regression. Here I don't have a classification 1, 2, 3, 4, 5, 6, 7, 8. Here I have something which is a case where I do not know what are these yi's, the labels. It can come in among any infinite values of r, for example. So I do not know the labels. Only I know the labels of n training vectors. And there's yi's are any element in R. These are no longer fixed 1, 2, 1, plus 1, minus 1, or 1, 2, k, something like that. So let us look at a car company. Car companies usually advertise. They advertise in TV, they advertise in newspaper, and of course in social media like YouTube and other places, in Facebook and all these places. So we take data of sales for 20 cities. So advertising cost on TV in these 20 different cities and their sales. Advertisement cost in the newspaper and their sales. Sales is on the vertical one and advertisement cost is on the horizontal one. Similarly, for the social media. It, so if you observe it, we now have to figure out, because I do not have any control on the sales, but I can control the advertisement cost. I can increase it, decrease it, whatever. Can we figure out from the given data if there is a possible relationship between the advertisements and the sales? Does it say that if I increase the advertisement cost, sales will go up? For example, in this particular city, where heavy advertisement cost was given on the social media, the sales did not go up compared to the one here where there was less. This particular city, so the 18th city or 19th city, this particular city where the advertisement cost was lesser than the previous city but had more sales. Now, can there be some relation that we can figure out, so we can make certain predictions of what the sales would be? That's what a car company needs. So these are called the input variables, or sometimes called the predictor variables. So all predictions are based on this, and this is a function. And why is the sales of the cars? Sorry, there's a mistake, it's not cars, it's cars. So we have to find a function from R3 to R such that I can write down this relationship. Y is a function of x1, x2, x3, those costs, plus some error. Of course, it may not exactly match the sales value for any x1, x2, x3 that you choose. Suppose you actually have seen x1, x2, x3 and you have seen what is the actual cost. You have put f, you construct a function f, you put in the value, okay, advertisement cost is in newspaper is this, TV is this, social media is this, and you get some value. But when the actual sales occur, you can know what is it there may not exactly match. So that difference is called the error, and that error usually is normally distributed with zero mean, right? We say that f represents a systemic information that x has about y. So that is why when you have a regression equation, you always put an error term, because you cannot exactly match what is the actual outcome in the field. You have to understand all these data, right? Sales, all these data that you get of advertisement costs, etc., on sales, TV. These are realizations of a random variable, because it depends how much money you will put on advertisement, depends on the current scenario of your company, economy, cart sales, demand, and so many things. So those are random things, those are unknown, and we always assume that these actual x1, x2, x3, there's those costs that you will put in to advertisement, those are actually realizations of a random variable. You decide those costs based on the scenario. So these are all random variables. So more precisely, if you want to write down, then x1, x2, xn are particular values of the random variables capital X1, X2, Xn. So these are more, because one might think, oh, this is just a variable x, this is a random variable, it looks so stupid. How can you take an ordinary function, normal real valued function, add it to a random variable? Okay. But actually, these functions are also random functions of random variables. So they are random variables themselves. So to be more precise, for example, y, the sales, you do not know ahead what is the sales value. So those are also depending on scenario. When the actual sales come, they are realizations of some random variable capital Y. So the regression equation should actually be written in this form if you want to be more erudite. In most cases, it's very difficult to find the function f. It's a very difficult job. So what I want to do is kind of find a function f hat which estimates that f. So f hat allows to predict y by y hat, and then we have to see what is the expected error, because now we know that these are all random variables. No data that you get in real life is deterministic data in general. Most of the data are realizations of some random variables. So essentially those data are the random sample in most cases. So y minus y hat, the expected value of the square of this, the square error, that needs to be figured out first. That if I have constructed this function f hat to estimate f in this process which you call regression. So regress means to step back. You don't know the actual function, step back and just find f hat. That will be enough. So here, if you do the calculations, knowing the definition of variance and knowing that expected value of epsilon random variable is 0, then I can write down this whole thing, if you look at it very carefully, into this. Because if for the moment, if I fix my random variable x and I fix my f hat is fixed, then this is what I get. This is the final expression, because here I will do expectation epsilon whole square minus, that will be 0, minus 0. 0 is nothing but e of epsilon. So this will give me variance of epsilon. This error can be reduced. You can choose f hat in such a way so that f minus f hat, that difference for a given x, comes down. But this is beyond your control. Any error which is a random error in this particular case is beyond our control. So when you do a measurement, when you even measure a line, you draw a straight line and you measure it. If you really measure it properly, if you really do it 5 times, every time there will be some little difference, and maybe you will make it more precise or will get less precise. So there will be always a little error, and that error comes largely, those are chance errors, and that cannot be reduced. That's not in our control. But what is in our control is this, then that can be reduced. Okay. So one of the most important type of predictor functions is the linear prediction. For example, if I look at this data, a straight line, I can draw a straight line, for example, to these points. Here I can draw a straight line through much more points. So here it will be a better straight line fit. So in many cases we try out a linear function as your predictor function or regression function, which is called linear regression. Right? So a linear function is written in terms of inner product, where w is something we have to figure out. So finding out f hat is same as finding w. So basically we have to look at y hat into wx. So wx is wx1 plus w, whatever be x1, x2, x, then you give it, will give me some y hat. So you understand that we have to now reduce the training error. So suppose you are given xi, yi, x1, x2, xn, y1, x11, x12, xn, y1, the same thing. Suppose you have two variables and you are working in R2, then you have x1, y1, x2, y2, x3, y3, that you have already learned in many of your statistics classes. So basically this is the training data. Now you find this w based on the training data by minimizing the training error, and then try to see if you get the test data what this w is giving. Is it actually doing a good thing or doing a bad thing? That's the whole thing. So this is the training error. I have taken an average of the square training error, that's called the mean square error. So I have written it in terms of the sum of the square errors, which can be now written in terms of the norm. Y hat train means y hat training means y training means y1, y2 dot 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 and up to yn. And y hat means when I am computing this y hat, I am actually putting these values on x1, x2, xn, x11, x12, x1n. Then it will give me y hat 1. Then I will have y hat 2. So that is what it means. So y hat training means it is a vector whose components are y hat y hat training I. So for the ith feature vector, you are basically putting in those in this linear function and you are getting out that y hat I. So basically when you write the linear, when you write the thing as a linear function and you know what are the training data, then if you write down for say y hat I is w1 xi1 wn dot dot xin, then this is actually written in this matrix form ax, basically y hat equal to ax. Now we really have to handle this optimization problem. Why you should be training here? So this is your this is your estimate of the actual f which you do not know. So you are telling that maybe that actual f is a linear function. I assume that possibly it is. I'm using that to estimate, get some idea about the actual function. So I'm trying to find the predictor. So a lot of effort is gone given in regression to find this f hat, that estimating function. So here f hat is this. So but here there will be y train. So now if this matrix has linearly independent columns, then we can we'll show it later on when we study least square problems, that this w vector can be computed in this form absolutely neatly. Now observe that this w is independent of m. It doesn't matter what is the number of training examples that you have chosen or elements in the training set, your answer is always the same. It simply dependent on the matrix X. Okay, so I cannot say W is completely independent of M. W, it doesn't matter whatever be the W. Of course, W depends on the M in the sense that it depends on X, of course. So once you know these vectors, once you can compute this, it doesn't matter. That's not a correct writing. It doesn't matter what is your size of X actually. You can always compute W in this way. So it is not that if M is something very big, I cannot compute W. This is not a correct line. What I should say that it doesn't matter whatever with the M, W can always be, this W vector can always be computed like this. Okay. Sometimes we often write it in this form, that every y hat, every vector, prediction vectors give is nothing but wx plus b, where w x is the linear part and b is the translate, which gives me the affine function. Sometimes this is also spoken as linear functions in linear regression. Doesn't matter, but you can also use affine functions, because when you take the difference between the two, this b will get cancelled. When you take y hat training minus y training, this will get cancelled, this b. So now we'll come to this environment called an operational environment of the training algorithm or the function that you are going to figure out. One is supervised learning and one is unsupervised learning. Supervised learning is the one which we had just discussed, classification and regression, because there we will talk about that given a feature vector, there is always a label or a category attached to it. But in unsupervised learning, nothing is known. Sometimes in medical setup, what happens that you have supervised learning, but some of the labels of the training set are missing. Then you have to have several different functions you have to make to have a better idea about the training set itself. So that's a complicated matter. We'll not get into it. So the whole point is now there is something called unsupervised learning. Unsupervised means I have a training set, I have the feature vectors but don't know the label. But you have to learn about the data from that feature vectors without bothering about the labels. So how would we does that kind of learning is also important. But supervised learning is very, very popular, like the generalized additive models and the support vector machine, which is a very important class of classification approaches. That comes under supervised category of supervised learning. So support vector machines are the first real game of machine learning where you can use mathematical optimization beautifully to do your classification, and it works pretty well. Unsupervised learning looks like a blind alley. I do not know anything about the functions, then I try some way to learn about the functions, and one of the techniques is called clustering techniques. For example, there is an example in the book by this on statistical learning of the four authors, of which Steve Tijani is one of the authors. So suppose there is a mall and you have data about customers visiting a particular mall. So family income, postal code, and frequency of arrival. Now, from this information, can you gauge that this is a high spender or low spender? So we can, given a feature, we ourselves create categories and put them into some categories, which could be reasonable looking at the data. That if your family income is very high and the postal code looks like they are staying in a posh area, but the frequency is not very high, then we might still think about putting them in a high spending room. But the family income is very low and they come from, say, a housing area where it's possibly, you might be angry if I say it's not posh, but some housing area where maybe you have this flats for middle class people, but they frequently come there. That doesn't mean that they get into high spending one. They might be high spenders. Of course, there is no data about them spending here. So data seems to be incomplete. But somehow we may try to do that classification. Okay, this family is high spending, this family is not so high spending. It could be that there is a person with high family income living in a very posh area, but coming very frequently to the mall but not spending. So these are very dicey type of things, but still you can try to make a reasonable classification. Ultimately, the goal is to classify, right? So how to have this, do this clustering? One cluster of, say, spending high, another say cluster of medium level spending, low spending, whatever. You can have several clusters. Now, given every data, can you do it manually? No. So there must be some automated clustering techniques. Such an approach is called the principal component analysis, which we shall discuss later. And with this, I stop my basic introduction to machine learning. And in the next class, we will get into basic optimization. Very basic optimization. But before I go to optimization, I will first talk about derivatives. It's very important that we have a hold over derivatives, and then we will get into optimization proper, steepest descent algorithms and their use, and later on we will come to stochastic gradients and all, stochastic gradient descent and all those things. So steepest descent and gradient descent. So those basic algorithms of optimization has to be understood in order to gain more foothold into what we are going to do. And of course, a lot of important problems like this, what is that called? This regularization problems, where you have to regularize of objective with some additional functions. So lasso problems, those kind of problems, which is regularized problem, those kind of things would be important in machine learning, and we will gradually discuss those. So see you this week again. At the end of this week, we will speak about derivatives. Thank you very much.